Hello, this is Neil.
And I'm Daniel.
This is our contribution video for ME190. So my contribution to the project was acquiring a test vehicle, which was bought through Amazon, and I also acquired the speed controller, which is an L298N driver board, because I thought that would work well for our needs. From there, I built the vehicle and soldered major connections like the motors. They need wires, and then the ground wires and stuff like that. And from after the vehicle was built, we tested the open loop function of our plant. This has let us figure out how fast the heatsink would heat up, and from there we can figure out how to make a response to match it. Using a reasonable percent overshoot and settling time, I calculated the time constant, zeta, natural circular frequency, and response to the system. From there I calculated the theoretical values for the PI controller, KP and KI.
Okay. So, and my contributions included programming the Arduino and designing the circuitry. By that I mean figuring out which pins to use and how to connect them to the driver board. I also tested the program to make sure it could actually read the temperature sensor and also drive the motor board properly. I also created the MATLAB program that could log and graph the temperature data, which we read from the Arduino, and I assisted in testing the open loop function and determining what the time constant was for our open loop plant. Afterwards, I generated a Simulink model to try and find other values for the PI controller that we could use that were quicker than our calculated ones, but also even better than the ones that Simulink would calculate for us.
So that's the end of our contribution video.
We have to mention what we learned from this.
Oh man.
Yeah. So some of the things we did learn from this project is that when you have a really slow plant, it can be very difficult to try and control it. We did find PI values that would allow us to reach a temperature without any overshoot. Some of them even with a little overshoot, but they would take way too long for the system to reach equilibrium, and the wheels wouldn't be running for most of the time. Which one of the things was we wanted the wheels to actually still be able to move, but maintain a temperature, a safe temperature.
Yeah. So what we can learn through this is like we can test and we can build a PI controller to meet our system requirements, and we do have the data available to show that the controller that we've calculated will be able to meet our requirements, but it's not in the same time scale as a controller that we can just randomly figure out through testing, right? The time scale for our controller that we calculated would be around on the order of 6 hours or 12 hours, which is completely out of the time scale for, like, you know, something that needs to take 2 minutes to cycle through its system. So from ramp up to the cutoff to ramping down would take 2 minutes for our experimental system tested only through experimenting with the KP and KI values versus the calculated values for KP and KI, which would give us a time scale of 6 hours for it to cycle through, ramp up, and then get to the cutoff and then ramp down.
Yeah, in a way we were running with two different plants at two different intervals. It would heat up a lot faster than it could cool down, which would throw off our values as well. One of the things we could, we thought could have improved our project would be that adding a fan or even removing the heatsink, but we would probably still need a fan in order to help with the cooling process, make it quick. Let's see. What else did we learn?
Yeah, I don't think anything else.
Well, we did learn that while Simulink is a useful tool to help figure out what the PI values are, it's not going to be a perfect fit. It still requires some tinkering with the physical device itself to figure out the proper values.
I agree. So should we end the video?
Yeah.